Okay, so we have to start this topic, electrical capacitance of a conductor. When you're watching this video, please make sure if your notebook is with you, and please write notes. Now, what is electrical capacitance of a conductor? So let's first understand the basic theory, then we'll discuss it extensively. Now, electrical capacitance, what is it? Electrical capacitance of a conductor is a measure of its ability to hold electric charge. What does this mean? Now, we already know that when we have a conductor and we give some charge to this conductor, we have done this before. And when if we give some charge to this conductor would develop some potential. We know that is how we charge our mobile phone and everything. So when we give charge to a conductor, it develops a potential. That idea is very simple. We have done this before. Now, how much potential it is going to develop for how much charge given? That is what we have to understand. Okay. So assume that you have two different conductors. Different conductors means their size may be different, or their shape may also be different. Okay. And they may have made up of different material also. Might be this is made up of iron, this is copper. Okay, different material. Now let's say if you give 10q charge to this one and the same 10q charge to this one, positive 10q, let's say, and then you measure that the potential this conductor developed was, let's say, 1 volt, and this conductor developed a potential of 2 volt. Now then you can calculate that this conductor can hold 10q charge for 1 volt rise in potential, because you gave 10q charge to the conductor and it developed a potential of 1 volt. That means it can hold 10q charge for 1 volt, but this conductor could hold 10q charge for 2 volt. That would means 5q charge for 1 volt. So what we get, that this conductor develops a 1 volt potential. This conductor develops 1 volt potential when it is given 5q charge. So by this logic, we can say that this conductor has more capacitance. This is the meaning of the word capacitance. This word capacitance. Capacitance is it's a measure of ability. That means it's a characteristic of a conductor that decides how much charge it can hold for a 1 volt rise in potential. So this has a capacitance of 10q for 1 volt, and this has a capacitance of 5q per volt. Okay. Now let's read some theory here. So when an insulated conductor is given some charge, why the word insulated is here? So that this conductor is insulated. When you give the charge to the conductor, it will not flow anywhere. That is why the word insulated is here. Is given some charge, it acquires a certain potential, and if we increase the charge on the conductor, its potential also increases. We just did that. And if the charge q put on the insulated conductor increases, then the potential and charge would be directly proportional. That is, charge and potentials are directly proportional, and q is equal to c v. This c is the capacitance. This c is the capacitance. Now capacitance then would become charge over potential. Capacitance then will become charge over potential. What would be the standard definition? Capacitance of a conductor may be defined as charge required to increase potential of the conductor by unit amount. Unit amount means 1 volt here. Okay. Now take your time to think about this. You can go back and watch the video right from the beginning once again. Do this a couple of times because this is a very simple but very, very crucial idea, crucial concept that you must understand before progressing further. If you have any doubt over this, please watch the video once again till this point. If you are clear with this concept, then let's move on. Now, this capacitance, that is this ability of this conductor, it depends upon what? So first thing, it would depend upon the size and the shape of the conductor. So how a conductor looks like, it might be a sphere, it might be a cylinder, it may not be a symmetrical structure, maybe it's a non-symmetrical structure, it may have been a hollow structure, any kind of conductor. So shape and size. So capacitance depends upon the shape and the size. Then the next is nature of the permittivity of the surrounding medium. Now, in the previous chapter, we have discussed about this concept called permittivity of a medium. We have discussed this, and we discussed that permittivity of the medium is a property by which the medium would allow or restrict the electric field lines to exist. If you have any doubt, please go back and see the video once again, this permittivity video from the previous chapter. Now here, if you think that this conductor is placed in a certain medium, which have a certain permittivity, okay, so certain permittivity. So then thus capacitance of the medium would depend upon that permittivity also. And the next very interesting is the presence of other conductor. This is very interesting, and this will also be very crucial for the further concepts in this chapter. So presence of other conductor would mean something like this. So let's say if you have one sphere here and the capacitance of the sphere is C. If you bring another sphere nearby or another sphere nearby and more such spheres, then the capacitance of our original sphere would also change. So it depends upon whether this conductor is nearby other conductor or not. On that factor also, this capacitance depends on. Now, next point is it's worth noting that the capacitance of a conductor does not depend on the nature of the material. Okay, it does not depend upon the nature of the material. And it also does not depend upon the amount of charge existing on the conductor. Now, you will always have this particular conceptual dispute that, sir, how it does not depend upon the nature of the material, because a conductor can be a good conductor or not so good conductor. There are a variety of different conductors. Some have higher conductivity. I mean, conductivity is also a property of a conductor. So how does the capacitance have no whatsoever relation with the nature? So does it means it does not have any relation with the conductivity? This we will discuss later. Now, the amount of charge existing on the conductor, this point is important to you. See how the amount of charge existing on the conductor does not matter. We have just now done Q is equal to CB. C, that is the capacitance, happens to be the constant. So the ratio Q by V, the Q individually may change, that is the charge may change, and proportionately the value of V will also change, because capacitance is basically a ratio between Q and V. So it does not depend upon the amount of charge. A conductor may have a 10 q charge or may have 100,000 q charge, but that does not depend. The capacitance does not depend upon the amount of charge. Why? Because if the charge increases, proportionately this potential will also increase and the ratio will still be the same, that is C. Next, unit of capacitance. So the SI unit of capacitance is called farad, F-A-R-A-D, and it is written as capital F, farad, and it is named after the honor of Michael Faraday. It's a great physicist. Now, what is 1 farad? 1 farad. So what was our formula for capacitance? C is equal to Q over V. Q is charge, we know, and charge has a unit of coulomb. So 1 coulomb over 1 volt. So 1 farad is 1 coulomb over 1 volt. That is 1 coulomb over volt. 1 coulomb over volt. Now 1 farad is a very large unit of capacitance. 1 farad is a very large unit of capacitance. Why it is very large, we will be discussing. We will be discussing it in some time. But it is a very large unit of capacitance. So on a more applied basis or practical basis, you will find that the unit of farad that you are going to get mostly millifarad, microfarad, picofarad. In the numericals also you will find, rarely you will find any numerical that value of capacitance is given as 1 farad. Okay, every year whenever you find the unit of the value of capacitance, it would be stated in some smaller units. Dimension of capacitance, very simple. This 1 farad is equal to 1 coulomb over 1 volt. 1 coulomb is coulomb, you know, charge is equal to current into time. Okay, and volt is equal to again work done, that is joule over coulomb, and this coulomb will become square, and 1 coulomb square over 1 joule. You will get this as the unit, and then you can convert that into the dimension. Now, next topic is capacitance of an isolated spherical capacitor. Now, till now, we have been understanding about the term as capacitance. Remember, capacitance is a property. It's an ability. We discussed it before. It is an ability, measure of the ability to hold charge. But capacitor is a device, or it's an object. Capacitance is an ability, capacitor is a device or an object. So what is an isolated spherical capacitor? If you have a spherical capacitor which is not in contact with anything else, it is not connected to ground as well. Okay, it is not connected to ground, it is not connected to any other conductor. Okay, it is a completely isolated capacitor, and it is also considered to be in space. Okay, free space. We are going to calculate this whole thing on the basis of free space, and that is why we are going to use the value epsilon naught. Okay, now if you give some charge on this on this spherical conductor, which you now call it a capacitor as an object, it will develop some potential. So let's assume that you have given a charge of q charge, you have given positive q, and this has developed some potential. Now what is the potential this is going to develop? We have done this in previous chapter, in this previous topic, potential topic. We have done potential developed by the spherical conductor. So we know potential developed by the spherical conductor V is equal to 1 by 4 by epsilon naught. charge on the conductor divided by the radius of the conductor r. Okay. Now based upon this, we can calculate the capacitance. Capacitance was simply C was Q charge over volt or potential. And potential we just now calculated. So capacitance would become C is equal to Q by V and V is equal to 1 by 4 pi epsilon naught Q by R. You can take these two Q out and this 4 pi epsilon naught R will go on the top numerator and then your C will become 4 pi epsilon naught R. This also mean that capacitance is proportional to radius. Proportional to radius means if there is a larger capacitor, if there is a bigger capacitor, it will have more ability to hold a charge. Now, I hope most of you remember in the first chapter, there was a question. It's an NCERT concept that if you have A, B, two similar conductor having a charge Q, and you bring another similar conductor C with having no charge, and then you connect with A, it will this two conductor A and B is going to share the charge and share the charge Q by 2 Q by 2. We have done this question in class as well. If you don't know this question, if you don't happen to know this concept, then please go and do NCERT questions from previous chapters. Now this was only because this was similar conductor. Because these two conductors were similar, that is why they were holding charges equal Q by 2 Q by 2. What if the other conductor is bigger? Then they would not have been holding charges Q by 2 Q by 2. Then they would be holding the charge proportional to their radius, because the capacitance or the ability to hold charge is proportional to the radius. That is what we have just now understood. The capacitance of a spherical conductor is proportional to the radius. Now go back to this video beginning. Go from this point, capacitance of an isolated spherical conductor, and watch it once again. Okay, pause wherever you feel like and watch it once again. Now, next topic is this 1 farad. I told you when we were discussing about this farad thing, the definition. I told you then that this 1 farad is a very large unit, and it was very large unit. But why? Why it is a very large unit? Let's find out. Now look at this calculation. This is pretty simple. Let's assume that we have a spherical conductor, and this spherical conductor has the capacitance as 1 farad. So I am assuming it. Okay, I am assuming that this spherical conductor has a capacitance of 1 farad. Assumption. If that is true, or if my assumption is true, then what will be the radius of this conductor? What will be the radius of this conductor? Now, just now we have done this formula. We have done this formula that capacitance is equal to 4 pi epsilon naught R. If I assume this capacitance, this value to be 1 farad, the value of 4 pi epsilon naught R, what is this value? This value is 1 by 9 into 10 raised to 9. See, 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. This was 9 into 10 raised to 9. Obviously 4 pi epsilon naught will become 1 by 9 into 10 raised to 9. Very simple. Now if this is so, if this value is 1 by 4 pi epsilon naught r, then this radius should be 9 into 10 raised to 9. Then only these two cancel out and this will become 1 farad. That means the radius, the value of the radius should be 9 into 10 raised to 9. This value should be in meters, and meters means then I can convert it and say this is 9 into 10 raised to 6 kilometer. Now this is a very, very large radius. It is about 1500 times the radius of the earth. So 1 farad is a very large unit. It is not possible to have single isolated conductor of very large capacitance. You can have large capacitance, but not single. Multiple conductors can join and become very large, but single isolated capacitance cannot be very large. I mean, it cannot be 1 farad, because for that you need to have a object which is 1500 times the radius of that object will be 1500 times the radius of the earth.